Okay, so in this problem, we have that ethane is being chlorinated in a continuous reactor, and we're forming monochloroethane as our desired product. And then that product is being further chlorinated in an undesired reaction, which forms this undesired product here. And the selectivity of this desired product to this undesired product is 14 moles of monochloroethane per mole of C2H4Cl2. And as you can see here, this is supposed to be a 4. I corrected on your copy, but this is a 4 here for C2H4Cl2. And then, so what we're going to start off with, as always, is drawing out our process. So coming into the process, we have ethane and chlorine. So we have some mole amount of ethane, and then we have some mole amount of chlorine. And then coming out of the process, we have that we were told to take a basis of 100 moles of monochloroethane. So we know we have 100 moles of C2H5Cl. And then we have some number of moles of ethane still, unreacted ethane, some number of moles of HCl, and then some number of moles of the undesired side product, C2H4Cl2. And then, so we know we don't have any chlorine coming out because all the chlorine's consumed. And now we're gonna do a degree of freedom analysis based on atomic species method. So we have 5 unknowns. Those unknowns are N1 through N5. And we have 3 atomic species balances that we can do. That's on carbon, hydrogen, and chlorine. So we are left with 2 degrees of freedom. All right, so we got part A done. Now for part B, we are told that the reactor is designed to yield a 15% conversion of ethane, and there's a selectivity of 14 moles of monochloroethane to 1 per mole of undesired side product. And there's a negligible amount of chlorine in the product gas because we're assuming all the chlorine's consumed. And we are asked to calculate the feed ratio. And so the feed ratio is how many moles of Cl2 per mole of ethane, and the fractional yield of monochloroethane. So here what we're going to start off with is the selectivity. So using the selectivity, we know that 100 moles of monochloroethane equals 14 times N5, since N5 is this undesired side product. And then from that, we can get that N5 is equal to 7.143 moles of C2H4Cl2. And then we know we have 15% conversion of ethane. So that means that 85% of the ethane does not react, and that 85% of the ethane that doesn't react has to equal N3. So 1 minus 0.15, which is 0.85 of N1, has to equal N3. And we can relate, we need another equation to solve this. So we can use the carbon balance. And we know that 2 of N1 equals 2 times 100 plus 2 times N3 plus, it's also present in N5, and so plus 2 times 7.143. And I'm not going to show it being worked out, but if you solve this equation, plug this N3 equals 0.85 minus N1 into this equation, and then solve for N1, and then plug that in to solve for N3, you end up getting that N1 is equal to 714.3 moles of ethane in, and N3 is equal to 607.2 moles of ethane out. Okay, so we have N1, N3, N5. We still need N2 and N4. So what we're going to do now is hydrogen balance to get N4. So for our hydrogen balance, we have that 6 times N1 is equal to 5 times 100 plus 6 times N3, which is 607.2, plus N4 plus 4 times N5, which is 7.143. And we also have N1 is equal to 714.3. And when you plug this in, you end up getting that N4 is equal to 114 moles of HCl. Now we want N2, so we're obviously going to do a Cl2 balance since N2 is only Cl2, or chlorine. So chlorine balance, we have that 2 of N2 is equal to 100 plus N4, which is 114, plus 2 times N5, which is 7.143. And when you plug that in, you end up getting that N2 is equal to 114 moles of Cl2 as well. Actually, that's our final answer. I'm not gonna box that in. Okay, so now we are going to figure out our feed ratio. And our feed ratio is just going to be 114 moles of Cl2 per 714.3 moles of C2H6. So there's 0.16 moles of Cl2 per mole of C2H6.